Hey guys, so some people are asking me how to make this spreadsheet. So I'll go through it real quick. It's pretty straightforward, but I wrote down some notes just to try and make this video go smoothly, as quickly as possible, and be as educational as possible, and not take up a lot of your time. So on the left-hand side, I've got this categorized. So boost air density, ambient air density. Okay. And I'm going to go through how to make this spreadsheet real quick, and then we'll talk about the significance of everything on the spreadsheet. So starting with boost air density, this calculation is the same on both sides. The only thing missing on the ambient air density is this column here for boost. Obviously, we don't care about boost on the ambient air density, so we're comparing what ambient air density is versus what it is inside the manifold. So the math will be the same for both sides. The only difference will be we'll be taking off this boost side. So we're just going to talk about this, and then you can basically build this exactly the same way and copy and paste essentially. So the first thing we need to do is I'm not going to go into the Anton equation. I'm just going to tell you what the values are. If your manifold air temperature is between 33.8 degrees and 212 degrees, which it should be, if you're greater than 212 degrees inside your manifold, you're basically going to be in having detonation issues unless you have really high octane fuel, or a lot of basically a lot of octane, or there's different types of fuels that can get away with it, but again, we'll talk about why. In the last video I kind of talked about why that's a bad thing, but anyway, so this should get everybody, at least most everybody, but you can actually go online and get the different numbers for Alpha, Bravo, and Charlie on this that are applicable to a different temperature range. So the first thing, and again, I got this separated into atmospheric and manifold, but we talked about what the differences are. And don't let this math scare you if you're not a math guy. This is the Excel will do all of this for you. You just put in the stuff I tell you and it'll be right. So first thing we got to do is find the vapor pressure. Okay. And again, I did a video on air density, so I'm not really going to go into why we do the different formulas in this video. I'm just going to tell you how to build it. So find vapor pressure. You're going to input these values, okay? Alpha, Bravo, Charlie, those values right there, okay? The next thing you got to do is this formula, okay? Temperature converted to Celsius, and then your absolute vapor pressure is going to be in those units. Just don't worry about units. We're going to be doing the conversions in Excel, so it really doesn't matter. We're going to convert our temperature to Celsius for the formula, because that's what these numbers are all based off of, and then we'll do this formula inside of Excel. So you can screenshot this and do it in Excel, but basically what we're going to do is you're going to go in here, and this is going to be a blank cell. This is where you input. Okay, you can input whatever you want here, and then you're just going to do a simple conversion. Okay, the conversion is just basically going to be temperature Fahrenheit minus 32 degrees multiplied by 5/9. Okay, and then that'll give you your degrees Celsius. Then to do your vapor pressure, this is the formula you're going to need. Okay, you're going to do power. Okay, and we'll just let me click on it here so you can highlight all the cells. Okay, but this is the formula here. Okay, so a log base 10, in order to get the log base 10 of a value, you're just going to raise this. You're just going to raise this up as an exponential, and I'm not going to get into the math, but it's just going to be an exponential. So you're going to do power equals base 10. Okay, you're basically just taking 10 and raising it to this part of the equation. Okay, and that'll give you your answer, and that's just algebra. But anyway, so power, and then you do the parentheses, 10, comma, and then this is going to be your formula. So alpha right? And then you're going to minus Bravo over Charlie plus Tango, which is temperature. And the temperature that you're going to be using is your degrees Celsius. Okay? So once you do that, that's going to give you your mmHg. And then you're going to convert that to pounds per square inch absolute. And so it's a simple conversion, just going to take that value and then you're going to divide it by 51.715. Okay? Simple. Not bad. Alright, so that's going to get you your units in PSIA. Then you're going to find your partial pressure. Okay? Let me scroll this down. Then you're going to find your partial pressure. And this is going to be, ignore some of this stuff. I'm doing some programming and actually building a component that I can use this to do live data in my truck. So ignore some of the sensor and stuff like that. This will do the same thing, just basically a point in time versus live data. So you're going to do partial pressure divided by vapor pressure. Okay, so basically you're going to input humidity here is just going to be whatever value it is where you're at, percent humidity. And again, I've talked about this. Don't use the one that you get from the Weather Channel because that's going to be corrected to sea level. It's not going to be accurate. You need to use the absolute humidity percent in your area. Then you're going to do the math for your partial pressure. And it's as simple as humidity multiplied by your vapor pressure. And that'll give you your partial pressure. Okay. Then you're just going to input boost. It's just going to be a value that you put in. Okay, see, I just typed in 9, and for now we'll just take that out because I'll tell you why in just a minute. And then atmospheric pressure. Okay, this is going to be what you input. And again, don't use the atmospheric pressure that they tell you in the Weather Channel. Use your absolute air pressure where you're at, otherwise this is not significant. Then you're just going to convert that to PSIA from inches of mercury, which is going to be basically inches of mercury divided by 2.036. And just to show you the cells, it's going to highlight your inches of mercury and divide it by 2.036. Okay. Then your air density. Okay. So air density is going to be this long looking thing, but really it's simple. Find air density. Okay. Your density is going to be equal to your atmospheric pressure minus your partial pressure times 144 divided by R, which is this 53.5 foot-pounds per degree Rankine, times atmospheric temperature, which is whatever the temperature is outside, plus 459.67. That converts it to degrees Rankine in absolute scale. And then that'll give you your air density. So all you're going to do is you're just basically going to type that out. And I'm not going to read that to you. You can pause and screenshot, but basically you're just going to take your degrees Fahrenheit, add 459.67. This 53.5 is a fixed value. 144 just converts it, converts units. So that's going to be a fixed number. And then your Bravo 10 is going to be your PSIA calculation for partial pressure, and then boost pressure that you input. The difference here is the boost air density is going to add, see, this is atmospheric side over here. So we're doing manifold side. So the only thing, like I said, the only thing that's different in this whole thing is you're adding, so you're going your pressure at your atmospheric pressure plus your manifold pressure in PSIG, your gauge pressure that's inside of your manifold. And then you're going to minus your partial pressure. So over here, the only difference is we don't have that manifold pressure that we're adding in. So this whole 2-column thing over here, whoops, this is all just the same thing basically on both sides for the most part. The only difference being mostly is that manifold pressure added. So you're gonna do this long thing. Now, in the last video I kind of talked about the percent day, and how this percent day is going to be basically you're comparing to J1349 standard. Now, that's how a few people do it. It's not how I do it, but that is going to be if you're trying to compare whatever you're building to a production vehicle, which in my mind, in my world, doesn't matter. I'm comparing it to myself. Basically, how efficient is my blower, which is all this thing is designed to do. So the percent day is just a change in, so basically you're just going to do 1 plus the boost air density minus the ambient air density divided by ambient air density. So this is just a percent change. It gives you the total percent change. And this is basically, this percent day here is just telling you how much additional air density are you adding in percent over ambient. And this kind of tells you how efficient your blower is. Now, this boost air density and this ambient air density, I calculate separately. And this table in the middle, and I'm going to unhide all this, and I'm going to show you all I've done. Okay, it looks convoluted, but all I've done here is done this math, but for each boost level, and I basically just did all the same math all the way across. Okay, so real quickly, air density is going to be the same math. Okay, your pressure and PSIA, the real IETs, basically what intake air temperature are you seeing on your gauge when you're at these various boost levels. Partial pressure, okay, and it's basically the same math, and then there's the formula there, but those are just looking at my cells, so you can screenshot that and look at the values I have in my cells. But it's the same math as over here. All I'm doing is, instead of doing a fixed value that I input temperature, humidity, and pressure, and then a boost level, and it tells me the ambient air density in percent day, I just do it over here, and I do it for every boost level so that I don't have to do this. The only reason I have this even here is so that if I wanted to make a pulley, see these crank pulleys right here? So that's my crankshaft pulley, how many teeth? And these are the only supercharger pulleys that are manufactured for my blower shop 192. So this is the part that's specific to my blower. And these horsepower to turn the blower, that's how much horsepower it takes to turn my blower at these various pulley ratios. So these are going to be specific to the blower shop 192. Okay. They're going to be similar horsepowers to turn blowers at similar ratios, but when you start getting into 671s, 871s, 1471s, they're going to take more horsepower to turn at the various blower speeds. You don't spin a 671 at 2 times. Usually you kind of max those things out at like 20% overdriven. You get beyond that, you start really pumping some heat in. But again, that depends on application, and that's kind of a general rule of thumb and not absolute. So anyway, this is just the same math, and I'm just doing it across. So basically how I did vapor pressure here, vapor pressure is calculated here. Okay, vapor and PSI, it's just the same thing, just converted here. So it's a whole separate column. Partial pressure, okay, that's this calculation. It's just in its own column. And then ignore these right here for just a minute. And this real IET, so this calculated IET I taught in how to do this. This is the ideal temperature at the discharge of the supercharger if it was just discharging air and not into a manifold, or into a manifold but not a heat-soaked manifold. If the manifold was just basically ambient air temperature and you're just looking at the discharge temperature of the blower, that's what this number would be. So this is what that blower discharge temperature actually is. But because that supercharger is in a heat-soaked environment and the rotors get hot, the casing gets hot, and everything heats up, it expands more and generates more pressure and more heat. And that's where this, basically right here, this partial pressure, that's where this comes in. So what you're looking at here is this is how many pounds of boost you're generating that is not being used to make horsepower. So at 10 pounds of boost, my effective boost is basically 10 minus this number. Okay, and that's really what you're getting into here. What boost is, okay, this is my this is absolute pressure outside. I'm adding a gauge pressure on top of that, and I'm subtracting this partial pressure. And this partial pressure is due to the temperature expansion, okay? That's how many pounds of boost is just from the additional heat added to the system, okay? So that's where this methanol cooling or intercooler, cooling from intercooler or methanol, this is where if you can get these IETs down, if you can get these IETs down, which with my methanol configuration right now, I usually get about 30 degrees Fahrenheit on average throughout the entire pool. You know, if you look at this, this is my fastest run in Old Red at 7.8 second eighth mile. You look at this IET data, okay, and I'll just do it from basically as soon as the methanol kicks in, which is as soon as I'm on full boost, to whenever I let off the throttle. And I'll hit this button, and my average temperature was 156 degrees. Okay, so that was at 9 pounds of boost. Okay, come over here, real IATs, 153 degrees. That's within 3 degrees. I'm good with that. So that's the average temperature throughout the whole run. And so that's a pretty good number. And the only difference for my real IATs is I'm essentially adding 15 degrees Fahrenheit per pound of boost over whatever atmospheric temperature is. And that's pretty typical with root superchargers. Your average is between 10 and 15 degrees Fahrenheit per pound of boost. And so I just go on the top end of that and add 15 degrees, and it pretty much matches what my IAT data is, pretty close. Just because the smaller the supercharger, the faster you're spinning it, the more inefficient it's going to be. So like a 671 turning 1-to-1 ratio is not going to have, it's going to be closer to this number than it is to this number. They're just a more efficient because you're just turning it slower. You're not generating as much thermal expansion heat. So anyway, that's why I have a real IAT column. So all of my density calculations are based on real IATs, not the calculated ones, but I keep them here because this is the target, right? If I can cool it and get it closer to these temperatures, I'm going to maximize the horsepower. Basically, if at 8.5 pounds of boost, if I can get the temperature of my discharge of my blower, my IETs, to 90 degrees, I'm going to get the maximum amount of horsepower I can from that blower. But you can see I'm like much, much higher than that. And that's even with, that's not including this 30 degrees cooling. This 30 degrees cooling basically comes off of that. So look, if I take this and zero this out, you can see how temperatures get really dangerous really quick. So, and 9 pounds of boost, it's right here. And that's pretty average. So if I'm idling, just sitting at a red light, not in methanol, not on boost, just idling, I heat soak at about 175 to 180 degrees. So this is very close. And 175 is really what it sees. And that pulley that I have is really designed to make 8.5 pounds of boost. That run that I just saw, it runs 180, a little bit more. So, and just to show you that, we go over here. This isn't going to be really all that good because this is not full idle. It was on its way down, but you can see temperature's kind of leveled off a little bit right there. Let's look over here. And this is really where it heat soaked while I was sitting there at idle. It says 165 degrees. Over here it says 169 degrees, but it gets a little hotter than that. This data log isn't the full data log. I kind of just snipped a piece of it here. Here, open data log, and we'll just open that 7.8 second run. Real quick, just kind of show you the validity of this temperature. Let that run for a second. Okay, so that is it. That is how you do the density calculations, and you just run that. You only have to do one cell, and then you just drag and drop. Now the temperatures and stuff, I don't use these numbers. I basically use these right here, okay? And I just input whatever the temperature is outside, the pressure and humidity, and ignore this until I get an actual data log. And I have this calculation is the same as this one. The only difference is all of my boost air density is done in here, so I don't need this square over here. This temperature is literally looking at whatever I input here. So like, I don't want to screw you up. So if I click on that, it says R3. R3 is this temperature. So all these orange cells, anything you see orange is doing math. It's doing a calculation. If it's green, it's something that I just type in. So like drivetrain loss down here, 85%. It's actually it's worse than that really on my truck, but that's pretty much the average 15% drop. That's air fuel ratio, RPM, blower size, and the pulley ratio I calculated over here, so I don't need to do this. And then horsepower to turn the blower, and that tells you your horsepower potential and actual real world horsepower. And I just have horsepower potential as real world horsepower over here. And all I did was my crank pulley, my supercharger pulley ratio is just this divided by that. Horsepower to turn the blower, this is specific to the 192 blower shop blower, and you can ask the manufacturer for these numbers. And then you have horsepower potential. This is the math that I have done in other videos. I've done a whole video on how to calculate horsepower potential, but it's easier to see up here. It looks like a lot of stuff, but it's really not. It's not that bad. Look at my video on, I think I even referenced it in the last, basically what's your horsepower potential at different atmospheric conditions. And I go through the math on this. And I don't think I do it on here. No, I don't do it on here. Okay. So the rest of this stuff is just some density altitude thing. I'll talk about that in just a second. And don't worry about inputs, outputs, and stuff. That's just the math that I'm working on for a C++ programming thing. But anyway, so, all right. I'm pretty sure you guys can get through that. All it is the same math, just done over here, okay? So like your vapor pressure here, it's using these three numbers, and then the rest is going on over here, okay? And remember, that's your temperature Celsius. So I do the real IATs, and then I convert it to degrees Celsius. And that kind of is how the math works, okay? It does the same thing as it did over here that I showed you. I just did it in a big mass thing so you can see. And then what I did here is I just highlighted this. You go up here to conditional formatting, new rule, and you can highlight based on their values. And basically I just did the highest, so like if you click on here and you just go to conditional formatting and then manage rules, basically I just have one here that says in these different ranges, which this first rule is this first column, air density, and then the next one is percent day, and it just highlights blue for the highest value, okay? And so the highest air density will automatically highlight, and the highest percent day, which should be exactly the same as the air density, will highlight. And this air density I'm comparing not to J1349 standard, okay? I put it here just as reference, but I'm comparing it to what it is. So this is comparing what the actual air density is, this boost air density, calculated against ambient air density, okay? So even this day that I did a 7.88 second eighth mile, it was 104% day, which is a comparison to a J1349. So I started off with a little bit better air quality than the standard. And I'm gonna hide these cells now to make it a lot easier to see. Let me hide this. Vapor pressure, partial pressure, don't need those. This degrees Celsius, don't need that. And so this is just saying the horsepower potential of my blower at these different blower speeds, at these different boost levels. So that day that I did that run, I was running 9 pounds. I was running my 8.5 pound pulley. It just ended up making 9 pounds, which is not normal, but I think it's just something to do with the air density that day being better than normal. So it made a little bit more boost. Anyway, with lower air temperature, normally boost drops, but for whatever reason, I guess just because air density outside was pretty good. Basically it's saying my wheel horsepower was, that's not correct because I had 30-degree cooling. So it looks like I was close to 490 horsepower and I was really making 9 pounds. So, 495 maybe. So what it's telling me here is even though the best air density is at 7.5 pounds, this is something I want to make very clear. And somebody mentioned this. They were like, hey, just because you're making the most air density doesn't mean you can't make more horsepower. And that's absolutely true. What I want to make clear here is 7.5 pounds of boost has the highest amount of air density. But if you look here, we're talking very small margins of loss in air density. So according to this, if I would have ran my 10 pound of boost pulley that day, my goal for Old Red is to make 500 rear wheel horsepower. So I'm going to go to the dyno on a day that I have similar air density and run my 10 pound boost pulley, and I should be able to get 500 horsepower. So it's going to be close. Obviously this is not exact, but it's pretty dang close. Whenever I ran it on the dyno last time, it said 465 and I made 463, so it's pretty freaking close. Math is a powerful tool, but really getting this number, this drivetrain loss number, accurate is kind of the harder part. I usually lose about 120 horsepower, so I don't really do it as a percentage when I'm actually predicting what the horsepower is going to be. But if I take this and say 0%, why did you not change? Why is my calculator being silly? I didn't have it selected. My arm was on it. So if I put that at 0%, okay, that's how much drivetrain loss I'm saying in here. And actually these numbers aren't going off of that, so I would have to, actually I don't even have to do that. So 502 divided by 85%, that'd be 590. So it's telling me this 502 would be 590 wheel horsepower. And these 700 R4s are usually about 65 horsepower, but on a four-wheel drive, they can be up to 120 horsepower. So this is a pretty accurate amount of powertrain loss. That's between 65 and 120. So like I said, it's usually pretty close. But anyway, so this is just my specific supercharger, and discharge temperature of 168 degrees. you know, I saw on that 9-pound run an average 155 or whatever, 156. So this was pretty close. So yeah, I should be able to meet my 500 rear wheel horsepower goal depending on the air density the day that I do the run and which pulley I run. But that distinction I want to make is, yes, this is the best pulley to run for air density, but you still have to take into account CFM. The faster you turn the blower, the more CFM, the more available oxygen you're still going to have to make horsepower. So you can see 450 here, 490. So, you know, you're still picking up horsepower at 10 pounds. Oh, now you're going to start losing horsepower. So if I would have ran my 11.5-pound pulley that I have, then, and actually I don't even own this pulley. I don't need it. I have the 29 and the 33. I may end up buying it eventually depending on the air density, but that 11.5-pound pulley, I would have actually made the exact same horsepower at 8.5 pounds. And this makes a lot of sense because of temperature. And I'll show this one more time. If you look right here, this partial pressure, at 9 pounds of boost, I lose 2 psi of that 9 pounds of boost is being lost due to is basically based off thermal expansion. So if you go down here to this 11.5, you're over double. So you're 4.7, you're over double the pressure. So even though I'm making 11.5 pounds of boost, let's look right here. What's 11.5 minus 4.7? And now, what is 8.5 minus, I'm sorry, we'll do 9. What is 9? Sorry, I'm trying to hold the camera and look at the same time. Look at that. That is why you're losing horsepower with more boost. My effective boost at 9 pounds of boost is almost 7 pounds. And my effective boost at 11.5 pounds, due to the temperature over here of 190 degrees, and that's with my 30 degrees of cooling over here from methanol, my effective boost is less. It's 6.75, so it's just under, and that's why I'm making, even with all that additional CFM that it's making, it's not making any more horsepower. So anyway, this is something easy you can make and basically determine what blower speed you need to run to be safe, because this is a very safe area here. 130 degrees is really the best place to be. Anything more than 130 degrees, you got to start pulling timing. And so these numbers can actually get even worse because you're pulling a lot of timing. These horsepower figures are with perfect timing. You are using all the fuel. This 11.8 to 1, you're using all that fuel to make horsepower. And that's not always true. 11.8 to 1 is E10. So 12.5 to 1, 12.5 to 12.8 to 1 is where you make your peak horsepower on straight gasoline. And when you're on E10, which is most of your pump gas these days, it's actually more like 11.8. So I command 11.8 to 1 at peak power. At my RPMs and all that for peak power, I target 11.8 to 1. And you can see that on my runs here. Let's see, right here. So this is AFR, actual and target. So if you look, AFR value is 11.8 to 1, 11.7. So it's basically right on 11.8 to 1, and you can tell right here when I hit my chip and I shifted, you know, there was a little bit of a blip here versus, you know, I was at 12.3 to 1, a little lean versus the target AFR of 11.8. But it stayed pretty much 11.8 the whole time. So that was what I was commanding. And then, so down here, the only other thing I haven't talked about is density altitude. This is something that if you have a draggy like I have, or other tools, drag strips will tell you what the density altitude is. This is really for airplane guys, and it doesn't really tell you a lot. The reason why I tell you this density altitude thing is kind of not as helpful as density is it does not take into account humidity. Density altitude does not take into account humidity. I repeat, does not take into account humidity. This is how you calculate it. A lot of people don't know how to calculate it. Let me make it easy for you. That's how you calculate density altitude. And you do the math. It's pretty simple. I may just make a separate quick video on this for people that are just looking for density altitude, because I know a lot of people don't know how to calculate it. It's pretty simple. First thing you gotta do is get your pressure altitude. And then that's just be pressure altitude equals 29.92. That's a fixed value that you're going to always reference to. That's an aeronautical thing. I'm not going to get into why. Minus AP, which is going to be your atmospheric pressure. Ignore sensor. This is just how I'm going to program mine in to give me my live density altitude. And then multiply that by 1,000. And then you're going to add your current elevation in here. Okay, that'll give you your pressure altitude. Then you go down here and you do density altitude equals your pressure altitude plus 120, so that's going to be a fixed value, times your outside air temperature minus the standard temperature for a given altitude. And I'm not going to tell you how you do this, but I'm going to tell you how to do it, but I'm not going to tell you why it's correct. You just have to trust me. You can look it up yourself. The standard temperature for a given altitude is going to be 59 minus 3.5 times your current elevation divided by 1,000. This is correct. You can look it up, but basically you lose 3.5 degrees temperature per 1,000 foot of elevation. That's all it is. So this is your standard temperature for sea level, and then you're going to lose 3.5 degrees per 1,000 foot of elevation. Okay, so my current elevation for this run was 708. That's whenever I did my 7.8 second eighth. And you're gonna do your pressure altitude, which is all that math I just explained. There's your screenshot. And then your standard temperature for a given altitude is just gonna be that number, 59 minus B25, which is just gonna be my standard, B25. That is my elevation divided by 1,000 times 3.5. I just rearranged it. But my current elevation, which I just input whatever it is, and then you divide that by 1,000, multiply that by 3.5, that gets you a percentage of 3.5 degrees, and you're going to add that to the subtract that from the 59, and that gives you your pressure altitude. And then you just calculate your density altitude, and that's just that same math. Basically is going to be your pressure altitude plus 120 times R3 on mine, and that's it. So yeah, hope you guys like that, and that was informational for you.